We're going to be looking at the climate data that we can get from ice cores. Ice core data given every year can give us an indication of what the climate was like tens or even hundreds of thousands of years ago and further. And we can get ideas of what the carbon dioxide content was like, methane, and then even temperature markers. So some things to look at when dealing with this. And I'm going to go ahead and take you through a little presentation to explain how exactly this works. So this graph is the graph we're working with in part one. It is from ice cores from Greenland. And what they did was they took samples of the atmospheric carbon dioxide and the oxygen isotope ratios to give temperature and overlaid them on the same maps or graphs so that we can actually get a better look at them. A couple of things to note here. First of all, the first thing we actually notice from this graph, if you look at this graph close enough, that temperature rises first and then carbon dioxide follows. And if you look really closely, you'll see temperature rise first and temperature fall first and carbon dioxide follow. So the first thing we note then is that carbon dioxide and temperature are directly related to one another. And that's really the answer to number one. And number two, the answer then would be temperature leads carbon dioxide. What causes this? Well, actually, as temperature increases, the level of carbon dioxide in the atmosphere increases because when the oceans heat up and when ocean water warms, it actually releases carbon dioxide into the atmosphere. When the ocean water cools, it actually absorbs carbon dioxide. And this has been responsible probably for the runaway greenhouse effect on Venus and the runaway refrigerator effect on Mars. Turns out that Earth is, of course, right in between them in the so-called Goldilocks zone around our sun, which is a very just right area. Now, why is it significant that carbon dioxide is rising and falling? Well, carbon dioxide is actually a greenhouse gas, and greenhouse gases are gases that absorb heat and therefore warm the planet. CO2 is not the only greenhouse gas. Methane is a powerful greenhouse gas, and so too is water vapor. Greenhouse gases are actually necessary to keep the atmospheric temperature stable on our planet, and they're necessary for life on Earth as we know it. If we didn't have greenhouse gases, the temperature would be well below zero all the time. So this is a good thing. So greenhouse gas isn't really a bad word. It is of note that carbon dioxide is about 0.04% in our atmosphere by volume. The most abundant greenhouse gas is water vapor, anywhere from 0 to 4% in the atmosphere based on the water cycle, but the water vapor does absorb heat and thus is a greenhouse gas. So it's thought that as carbon dioxide increases in our atmosphere, it does help to heat the temperatures. And when there's more heat, more water vapor enters the atmosphere. Water vapor absorbs heat. So there's a little bit of a feedback loop there. But as you can see, these are very small amounts in our atmosphere compared to our nitrogen and oxygen. You compare us to our neighbors, Mars and Venus, who have a 96% carbon dioxide by volume in their atmosphere. It's pretty remarkable. One of the big differences about Earth is that there's life on Earth. And the life on Earth, specifically the little ocean organisms, they use calcium and carbonate in the water to build their shells. And so a lot of the carbon dioxide that may have been in the atmosphere today is locked up in the rocks thanks to life on Earth. Very interesting. Back to our graph here. It is of note then that the temperature rises at some points and falls at other points. And it's likely, if we're going to look at number three in our questions, that when the temperature rises, that we are in a so-called interglacial period. And when the temperature falls, we are in a glacial period. And that's when the temperature goes so low that ice actually begins to creep onto the land surface and be tied up on land. Why does the temperature, and what we see from this graph here is that temperature and carbon dioxide have fluctuated over time. They've been high and they've been low. What is causing the temperature to rise and fall then? If it's leading carbon dioxide, what's going on? Well, first off, notice the top part of this graph here, it shows orbital shape, less elliptical and more elliptical. Back in the 1970s and 80s, studies were done to find and discover that the Earth actually goes through orbital cycles. These are called Milankovitch cycles after a meteorologist who studied this. And, sorry, he's actually a mathematician, Milutin Milankovitch. But at any rate, he noted that the Earth goes through cycles where its orbit gets more or less elliptical. That's called eccentricity. The tilt of the Earth changes, obliquity, and the Earth wobbles on its axis, precession. These things go through cycles at 26,000, 41,000, and 100,000 years, and they sometimes cancel each other out. Other times they line up to help each other um, amplify either in the cold direction or the warm direction on Earth. More solar radiation on Earth gives a warm direction, and less solar radiation hitting the Earth's surface cooler. The sun also goes through maxima and minima. The sun has cycles as well, giving off more solar radiation, which is received by the Earth's surface, or less over time. Here's a map of the sun's maxima and minima as you look back in the last 500 years or so. Today, we are in a modern warming period. We would expect the sun to be more active, and it is. There was a period back in the 1600s where it's called the Maunder Minimum. It's also known as the Little Ice Age. And it's thought that the Earth was going to go back into an ice age at that point because there is such low temperatures. Volcanic activity is thought to be a part of this. And also the sun cycles are thought to be. But the Earth's orbital cycles and the sun drive temperature. And as if you look back on the last, say, 10,000 years of Earth history, there's a little ice age there. There's been warming and cooling periods cyclically throughout. Noting that at the beginning of the Holocene, which is kind of our modern era here, that our modern epoch, that the temperature was warmer than it is today. And then you get to that last glacial period as you get beyond 10,000 years ago. So back to our graph, that is actually reflected in this. You can see that there are parts that are warmer than today, and then you go back and then there's that deep drop in the temperature back from the last glacial period. So question number 4 asks, has the Earth seen fluctuations of temperature in the past? And obviously the answer is yes. And has the Earth been warmer today? Yes, it has. 125,000 years ago, 325,000 years ago, based on this data. Actually, if you look back at this data, the last million years or so, the Earth has fluctuated greatly in its temperature. If you go back to 5 million years ago, look at the graph, you can see that the Earth has actually been warmer, much warmer than it even is today, or even in the warm period. And if you go back 65 million years, this is the last graph we looked at was right about here, from here to here. If you trace the temperature markers back in the late Cretaceous and early Tertiary periods, the temperature was 10 degrees plus C warmer than it is today. Really, at that time in Earth history, the oceans were just water. There was no ice on Earth, and the oceans were so high that much of the central part of the U.S. was covered in, or the southern part of the U.S., I should say, Georgia, Alabama, they were underwater. Illinois had oceanfront property at that point. So temperature has been warmer in the past, and temperature fluctuates throughout time. We go back to our graph, and it says, based on this data, make a prediction where you think CO2 and temperature are headed in the next 1,000 years. And based on this data, you might say that the temperature is likely going to drop, but that's uncertain. And unfortunately, it's uncertain because there's a unnatural, I can say, spike in the CO2 levels. And recent times we've seen this spike because of, and it's likely because of humans burning fossil fuels for energy, causing an anthropogenic rise in CO2, anthropogenic human cause. CO2 concentration in the atmosphere has been increasing unusually since the mid 1800s, particularly since the Industrial Revolution. And most of that CO2 is energy related burning, about 80% of it. And we also look at the last 100 years of temperature, noting that it is rising more than usual. This is the last 1,000 years. Of course, remember, we had the mini ice age there, and temperature was cooler, so we'd expect to see more warm temperatures today, but nonetheless, it is rising. And when temperature rises, sea levels rise, uh, environments change for organisms, and sometimes this, especially if our CO2 levels increase too quickly, this warming could cause problems for species on Earth that are already under pressure because of human activity. So there are many effects of global warming, but if it's the global warming is too rapid, many ecosystems are threatened and pressured in an unusual way. So these are considerations. Really, folks, I think the bottom line here with these studies is that climate changes, that temperature does lead CO2 up and down throughout history, and it's likely going to continue to do that. It does that because the Earth goes through orbital cycles and the sun goes through cycles. The globe has been much warmer in the past than is today. Um, but human activity has really caused an increase in CO2, which is likely going to cause a warming that's faster than the Earth is used to. So environments are under pressure. Take home message, it's always really important to live synergistically with your environment, uh, so that you can kind of preserve the natural flow of things and we don't really get ourselves in the way. We haven't really learned much or done much to do that in the past. And humans really didn't think about climate change when they were building close to the ocean or in precarious land areas. But we need to get smart about how we are living with our environment because it does help moving forward, both in taking care of our environment and taking care of us as humans.